Okay, welcome to part 3 of our lecture video series for Wednesday, April 19th, where we look at how we can calculate pressure volume work. So let's start with just a little reminder about what is going on with pressure volume work and why we care about this in general in our thermochemistry analysis. So as a reminder, when we're talking about chemical systems, right, which are molecules themselves or molecules that are reacting, right, thinking about actual, material particles. When we look at any kind of work that could be done on a system or by a system, as mentioned earlier, the work that we're looking for or looking at in these situations is often work that comes from the expansion or compression of a fluid, typically a gas, which is why we call this pressure volume work. So let's kind of think about pressure, volume, and work in general just by looking at a little example. So let's look at balloons. So let's look at some kind of scenario, I don't know, A, where I have a balloon that is full of helium particles. And let's say that my system undergoes some kind of change such that the balloon expands. And we're assuming it's a closed system, so I'm not losing or gaining any helium particles. All that's happening is I am looking at a expansion process. So here's my initial system. Don't like how small I made that highlighter. All right, so here's our initial system. And here's our system at its new condition, or our system at final condition, or our final system. And let's think about what's going on with this process here. So this balloon expanded, right? And let's thinking about what's going on in this expansion process. So in the expansion process, the balloon is pushing against the external pressure of the atmosphere, which is our surroundings, in order to displace outward. And if you remember, kind of generally, work is force and displacement multiplied by one another. So we got to think about the direction of our displacement. Here, our displacement is outward as we are expanding. So we're away from our system. And the force that we are working here with is going to be equal and opposite to the force that we're fighting against in order for this expansion to happen. So if I am looking at what's going on here, I would say that the sign of my pressure volume work must be negative. So what does this mean? So that means that work is being done on the system, on the surroundings by the system. because we've got that pushing outward. We're working against that external pressure. So it would kind of be like, let's see here, if you were going to apply a force against some distance, let's assume that you are Sisyphus from the Greek mythology. For those of you that don't know, Sisyphus was punished by being forced to roll a boulder or push a giant boulder up a hill for eternity. So he would push with, great exertion this giant boulder upward a hill to the top of the hill, only for it to roll back down, and then he would restart that process, and that was kind of like his infinite punishment. Tale of Sisyphus. So here, if you are Sisyphus and you are pushing on that boulder, right, you are exerting the push force to displace the boulder or move it some distance away from you, right? Force applied over distance. So since you are exerting that push force against the boulder's mass, right, then you are the one that is doing work on the boulder. So in the same way here, in this balloon expanding, since it is pushing outward, then it is doing work on the surroundings. And remember, anytime we're talking about leaving or exiting the system or away from the system, that's when we use this negative sign. So that's expansion. What if we were to look at compression? So compression would be the exact inverse, right? Compression would be, I've got our balloon of helium, which undergoes some kind of change such that its volume is diminished now. Again, we're still assuming it's a closed system, so we are not looking at the volume of the balloon being decreased because our balloon itself is losing helium. We're looking at some other cause of that, and we can talk about these causes later, kind of intentionally being vague. So if I'm going to force this balloon to compress or change its volume, then what we see is that the external pressure of the atmosphere, aka the surroundings, is pushing inward on the balloon, causing a decrease in volume. So what does that mean about work and its sign? So in this case, because we have the displacement due to our contraction happening in toward our system, our helium particles are becoming closer together, then that means that the external pressure is pushing on our balloon and work is being done on our system. So the sign of work is positive. So work is done on system by the surroundings. So then what does that mean about how we can quantify pressure volume work? Like how would we calculate it? So let's go back to this kind of original physicsy definition of work, force applied over some distance. So in pressure volume work, let's think about what the force is and how we can measure distance, which comes from our work by definition is force applied over some distance. dropped a little vector hat. This notation doesn't make sense to you, it's okay, ignore it, just comes from physics. All right, so let's think about force. And then let's think about displacement. So in pressure volume work, the force here is going to be the pressure. And I've decided I'm not going to actually derive this. I can show it to you if you want to come see some physics in my office. But in general, you can understand that pressure itself is a push or a pull, right? Probably you think about pressure as a push. Like if you think about feeling bloated, you feel like that push on your intestines and doesn't feel good. So pressure is going to be our force. Now, let's think back to these little examples that we did here. Anytime we were looking at pressure, we were looking at the external pressure of the atmosphere because that is either what our system is working against or what our system is being affected by. So our force is our external pressure, specifically the change in external pressure. No, just pressure. Sorry, external pressure. So this is the pressure of the surroundings that are external to the system. Typically just atmospheric pressure. And now, how about the displacement? So displacement is being moved from one position to the next. So even though in each of these examples we do have movement in three directions, we're still being displaced, right? We still had this outward displacement away from our system, right? That's what's happening in our expansion. We are moving from some kind of central point out. And here in compression, we are moving inward or toward our system. So we know intrinsically then that the displacement is going to be substituted by how much our volume changed. So how much we moved outward by expanding or how much we were compressed inward by compression, that's going to be expressed by our change in volume. So displacement or change in position is really going to be change in volume of our system. So then if I were to put these together and think about the work all relative to my system, if I were to just put in pressure and volume, I would say that this is the pressure of the system internal times the change in volume of the system. However, as we saw in our examples here, when we look at the force, we typically think about it not in terms of like what pressure is going on inside the system, but actually like what kind of pressure that our system is working either against or being like what is the word I'm looking for? Subjected to under. And that's the external pressure of the lab, right? Atmospheric pressure typically. So if I were to rewrite this to take into account that this is for the surroundings, then I would have to just flip the sign. So I would see then a negative P external times change in volume of the system. In other words, pressure volume work is negative external pressure times the change in volume of my system. So this is how we can calculate pressure volume work in a chemical system. Okay, I'm going to break this section up into two parts. I do want to do a little practice example where we look at how we could use now this equation where we quantify work into actually quantifying or calculating work. So let's take this section 3 and split it up into another part. Let's do a little example, and then we'll move on into quantifying heat.